What's up? I'm Vin, and I'm going to go through the August 2025 Geometry Regents, and I'll leave a link to a copy of this Regents in the description below. Now let's get started. So first up, we have part 1, the multiple choice, and there's 24 questions here, and each question is worth 2 credits. Question 1, an equilateral triangle is continuously rotated around one of its altitudes. The three-dimensional object formed is, and we have these 4 options to choose from. So first what I'll do is I'll draw an equilateral triangle. This is a triangle that has 3 equal sides. So it looks something like this. And what we're going to do is we're going to continuously rotate this around one of its altitudes. And just know the altitude is the line segment that connects a vertex to the base of the opposite side, forming a right angle with the base. Okay, so this is the altitude that I'm going to look at here. And we're going to be spinning this equilateral triangle in this direction. Okay, so just imagine here that we're spinning this around and try to imagine what 3D shape would be formed. And the 3D shape that would be formed would be a cone. Okay, so we'd be looking at a cone, and that tells us here choice 1 is our answer. Question 2, on the set of axes below, quadrilateral BDGF is rotated 90 degrees clockwise about the origin and then reflected over the y-axis. The image of quadrilateral BDGF is quadrilateral MQSP. And over here we have side BD will always map onto, and we have these 4 options to choose from. So for this question, there's a nice way we could get right to the answer. So when they said this over here, when they said that the image of quadrilateral BDGF is quadrilateral MQSP, they told us the corresponding order of the points. So what I mean by that, when I look at side BD over here, so side BD, I look and see that B and D are in the first and second position of BDGF. So that means whatever side we're going to get as our answer in the next quadrilateral would have to also be in the first 2 positions here. So MQ would have to be the side that we're looking for here. And this is without doing any serious geometry here. Okay, this is just a nice little shortcut. Is when they say that a shape is the image of another shape, they have to write the letters in corresponding order. So that's a nice little shortcut to get right to the answer. But a more technical way to do this would be to actually go through the transformation. So if we take quadrilateral BDGF and we rotate it 90 degrees clockwise about the origin, we could actually take our paper. So if you're doing this like at the actual Regents and you have, the Regents paper in front of you, or whether it be a test paper or something, you could actually turn your paper 90 degrees clockwise. So that's towards the right like this, and that's 1 turn. Okay, and then this would tell us, if we pay attention here to, let's say we're talking about side BD. So side BD was over here, but if I rotate this shape here 90 degrees clockwise about the origin, that would put BD over here in this location. Okay, so notice now that it's going over here in this location. The quadrilateral, or specifically segment BD, was in quadrant 1, and now it's going to be in quadrant 4. But then next, if we reflect this over the y-axis, can you imagine here now, like if this side I just transfer it over here like this, so I just place it over here like this, and now I reflect over the y-axis, we could see here that if I mirror image flip this over, that it's going to land over here on MQ. So we could actually, turn our paper and get an idea of where it's going to land. But focusing on the order that the letters show up is a nice little shortcut to get right to the answer. Question 3, in right triangle JO, hypotenuse JO equals 31.8, and the measure of angle J equals 38 degrees. To the nearest tenth, the length of EJ is, and we have these 4 options to choose from. So for a question like this, you should absolutely draw this out. Okay, so we don't necessarily have to draw this to scale, but what I am going to draw here is a right triangle. And I'm just going to make sure here that everything matches up. So we have right triangle JOE, but the hypotenuse has to be labeled JO. So I'm going to put, let's say I'll put J over here and I'll put O over here, which tells us that E is where the right angle is located. Okay, so the hypotenuse has to be across from the right angle. That's how we know to put JO over here. I could have put J over here and O over here, because then E will still be in this location here. But this will be enough to help us get to the answer. So now I'm going to label the side JO, I'm going to label as 31.8 units long. And the measure of angle J, I'll put 38 degrees. And our goal here is to find to the nearest tenth the length of EJ. Okay, so EJ is over here. And now this is where trig comes in. I'm going to use the mnemonic SOHCAHTOA. And for this, the O stands for opposite, A stands for adjacent, H stands for hypotenuse. So what you do is you focus on the acute angle inside the right triangle, and you look at X and say, okay, X is right next to the angle. It is adjacent. Okay, so I'm just label this as adjacent. This is the side adjacent to the 38-degree angle, and 31.8 is across from the right angle. This is the hypotenuse. Okay, and I will just abbreviate those words here. And now you just have to think which trig function, sine, cosine, or tangent, uses adjacent and hypotenuse. Well, notice that the capital C here has AH next to it. So what this tells us that cosine, so this is how I think about these questions, cosine of any angle, okay, so any angle, I could say here theta, all right? The Greek letter theta is very popular for trig functions. So cosine of theta is equal to the ratio of the side adjacent to theta over the hypotenuse of the right triangle. So now I could use that idea to set this up. I'm going to say cosine of 38 degrees is equal to the side adjacent to 38 is x over the hypotenuse is 31.8. And now here I'm solving for x. And right now what I have is I have x divided by 31.8. So here I could just multiply both sides by 31.8. All right, and if that's a little bit tricky to do, you could also just call this cosine of 38 degrees over 1, and you could cross multiply. But you're still going to get x times 1 is x equals 31.8 times cosine of 38 degrees. All right, and for this, anytime you're multiplying a number by a trig function like this, you could just write the number in front as a coefficient. So now for this part, we'll type this in the calculator, and I'll assume that your calculator has been reset. So what you want to do is make sure for the Geometry Regents that you are in degree mode. So you press mode, and you go down over here to radian, you go over to degree and press enter. Okay, and then press second mode to quit. And notice on the main screen here that it says degree, and that's what we want to be in. So now I'm just going to write 31.8 times cosine of 38 degrees. Okay, and now we just press enter. And the question told us to round to the nearest tenth. And this number here is going to round to 25.1. So x equals, and rounding to the nearest tenth, you look over to the tenths place, which is immediately to the right of the decimal. We have a 0. To the right is a 5, so we're going to round up here and say x, once again, equals 25.1. Choice 2 is our answer. Question 4, the hemisphere below has a radius of 8 centimeters. And we have here to the nearest cubic centimeter, the volume of the hemisphere is, and we have these 4 options to choose from. So a hemisphere is half of a sphere. So if we were to go to the reference page at the back of the Regents, we could find that the volume of a full sphere is 4/3 pi r cubed. Okay, so this is the volume of a full sphere. So for this question, what we're going to do is we're going to say the volume of the hemisphere, so I'll just put a H here for hemisphere. The volume of the hemisphere is going to be 4/3 pi r cubed, okay, and the radius here they told us is 8 centimeters. So we have 4/3 pi, and I'll write this without the units, 4/3 pi times 8 to the third power. But once again, this formula is the volume of a full sphere. A hemisphere is half, so we have to just take this whole thing here and divide all of it by 2. So for this, on some calculators, you could just press alpha x, and this will pull up a blank fraction. Or what you could do is you press alpha y equals enter, and this will pull up a blank fraction on the TI-84 plus CE. So now I'm just going to write in 4/3. If I want, I could do another fraction. So I could do alpha y equals enter again, or alpha x if your calculator has that, and do 4/3. Hit the right arrow to get out. And then we have pi is second and this up arrow here. And then r is 8. And we're raising this to the third power, but dividing all of this by 2. All right, I like using the blank fractions here because it's very easy to mess up when you just press divide by, that you could mess up with the parentheses and it just throws the whole answer off. So now we should be getting here to the nearest cubic centimeter, we should be getting 1072. So once again, our volume to the nearest cubic centimeter is going to be 1072 cubic centimeters, which matches up with choice 3. Question 5, in parallelogram ABCD, diagonals AC and BD intersect at E. Which information is sufficient to prove ABCD is a rhombus? So for this one, let's start off by drawing out the parallelogram, but we want this to upgrade to a rhombus. So I'm just going to go ahead and draw a rhombus, which is a parallelogram with 4 sides equal. Okay, so we have 1, 2, 3, 4 sides that are equal, and this would make a rhombus. But now what I'm going to do is I'm actually going to write in the letters here. So let's say this is point A, and then we have point B, point C, and point D. Now, where we start and write A doesn't matter, but once we write A, we have to either go clockwise or counterclockwise, writing A, B, C, D. Like I wouldn't be able to say A, then B, and then put C over here in this lower right corner, and then D. I have to either go clockwise or counterclockwise when I write the letters in. And now they tell us diagonals AC, so I'm just going to draw in the diagonals AC and BD intersect at point E. So we want to know now which information is sufficient to prove ABCD is a rhombus. Now, when you have a rhombus, I'll just say over here, is a parallelogram. And what makes it special is that it has perpendicular diagonals. Okay, so the diagonals are perpendicular. So perpendicular diagonals. And what else I could show is either all 4 sides are congruent, which is never going to be an answer choice. Okay, we're never going to have one that says, hey, all 4 sides are the same, because that gets us to the answer too fast. But one way to prove a parallelogram is a rhombus is to say that 2 consecutive sides, so 2 sides that are consecutive, so 2 consecutive sides are congruent. Right? And the reason why you only have to show 2 consecutive sides are congruent is because in a parallelogram, opposite sides are congruent. So once I know these two are the same, like let's say BC I have marked with 1, AD would have to be equal to BC, and then CD would have to be equal to AB. So that's why all you have to show is 2 consecutive sides are congruent. So now let's run through all the answer choices here. So for choice 1, we have AE. So that's over here, this piece. So AE over here is congruent to EC. Well, this is true for any parallelogram. For any parallelogram, the diagonals, so I'll say over here, the diagonals bisect each other. Okay, that's actually one way to prove that a quadrilateral is a parallelogram. Okay, so here, since these 2 pieces are equal, that's not special for a rhombus. This is true for any parallelogram, and that includes parallelograms that are not rhombuses. Okay, so this is not enough to upgrade the parallelogram to a rhombus. But now let's look. AC is congruent to BD. This one is also no good. This is basically communicating here that over here, the diagonals are congruent. Okay, diagonals are congruent would upgrade a parallelogram to a rectangle. All right, if I draw a rectangle over here like this with 4 right angles, the diagonals are exactly the same length. Okay, so that would be true for a rectangle. This would, once again, if I start with a parallelogram and I show diagonals congruent, that upgrades my parallelogram to a rectangle. So now we're down to the last 2. So AB is perpendicular to BC. Well, if you have a parallelogram with a right angle, that makes a rectangle, not a rhombus. Okay, so that's not guaranteed to upgrade a parallelogram to a rhombus on its own. So now just by process of elimination, it has to be the last one, but let's see what's going on here. AC is perpendicular to BD. Well, I was saying before that to upgrade a parallelogram to a rhombus, you could show the parallelogram has perpendicular diagonals, which choice 4 is communicating, so this is our answer. Question 6, trapezoid Josh, shown below, has non-parallel sides JH and OS. The measure of angle J equals 65 degrees, the measure of angle O equals 30 degrees, and the measure of angle OSA equals 80 degrees. And we also have here the measure of angle SHU equals 60 degrees. And we want to find what is the measure of angle HSA. Okay, so that angle, if we look over here from H to S to A, that's highlighting this angle over here. Okay, so that's what we want. And I'm just clean that up a little bit. So we're looking for the measure of this angle over here. So let's think about what we know here. So they told us that this is a trapezoid. So JOSH is a trapezoid. And we were told here the non-parallel sides are JH. So JH and OS are not parallel. Well, the New York State standard for the definition of a trapezoid is that a trapezoid is a quadrilateral with at least one pair of parallel sides. So if these sides are non-parallel, then the other two sides of the trapezoid have to be parallel. So that means that HS has to be parallel to JO. And what that tells us is now we could start thinking about things like alternate interior angles and other ideas that pop up when you have parallel lines cut by a transversal. So the next thing that jumps out at me is that in this triangle over here, so let's say triangle OSA, we have two angles, but we're missing the third one. So what we could do is we could take 80 and 30 and add them. And this would give us, we would have 110 and subtract that sum from 180. And we get the left over here 70. Okay, so the missing angle down here is 70 degrees. But now we could show here that this angle we want and this angle here that we just found are alternate interior angles. See, if I draw in here, I have these two parallel lines and I come in like this and I draw in this Z shape here. Okay, so these make alternate interior angles. So the missing angle here has to be 70 degrees. Okay, so the measure of angle HSA is 70 degrees, choice 4. Question 7, in triangle ABC below, points D and E are on AB and CB respectively, such that DE is parallel to AC. If AD equals 8, DB equals 4, and DE equals 6, what is the length of AC? So for this question here, let's start by labeling. So we could put AD is equal to 8, we have DB is equal to 4, and then we have DE is equal to 6. So we have this one over here, and we want to know what is the length of AC. So for this question, we were told that DE is parallel to AC. So I know that these two segments here are parallel. And what that then allows us to say, it allows us to say that triangle BDE is similar to triangle BAC. And the reason why I know that's true here is that those two triangles here share angle B. And then when I have parallel lines cut by a transversal, the corresponding angles formed are congruent. So see over here that these two triangles, once again, have angle B in common. And then this angle here at A and this one here, this angle BDE, is the same as angle A. So the two triangles are similar by angle-angle similarity. So for a question like this, what you could do is you could draw the triangles separate. Okay, so I could put BDE like this, and I could draw the big triangle over here like this. So I'm going to say this is triangle, we'll call this triangle BAC. And now I'm just going to start labeling stuff here. So I have this side over here. So I'll just change colors here. We'll put this side is 4 units long, and this one is 6 units long. This down here, that what we're looking for, AC, is X. But now AB, I would have to add 8 plus 4 is 12. And now that I have all this stuff set up here, I could set up a proportion to solve. So let's say I do 4 over 6 is equal to, so I'm comparing the left side to the bottom, that would be equal to the left side over the bottom side, 12 over X. Now for this one, there's a few different ways we could go forward with this. We could just think to get from 4 to 12, we go times 3. So then 6 times 3 is 18. So I could get there like this. I could also cross multiply. So I could say 4 times X equals 12 times X. 4 times X is 4X. 12 times 6 is 72. And then I could just divide both sides by 4. And then if we do the division here, X is going to be equal to 18. Okay, so either way, we're going to be getting 18 down here. However, before we move on, I want to point out a very common mistake. So there are going to be a lot of students for a question like this that try to use the side splitter theorem. So they're going to say something like 4 over 8 equals, and then they're going to say 6 over X. And then when you cross multiply, you get 4X equals 48. They divide both sides by 4. And when they try to do it this way, they get X equals 12. But be careful. Choice 3 is a very dangerous bear trap. Okay, so for this question here, we cannot do this. All right, the reason why we can't use the side splitter theorem here is because we're not dealing with the values of BE and EC. If instead, let's say the question had said instead that instead of these values being given, let's say instead the question said that BE was equal to 6 and that we were looking for the length of EC, Then I could say 4 over 8 equals 6 over x. Then I would do this. The side splitter theorem only applies when you have parallel lines cutting both of the other sides of the triangle. So you see here, these are the parallel lines coming in, and they're cutting these two sides of the triangle. We would not apply the side splitter theorem to the actual parallel segments, okay? But that's a very common mistake. And if they design the question like this, you can guarantee they're going to have a wrong answer like this designed waiting for you. Question 8, on the set of axes below, circle C has a center with coordinates 2, -1. And we want to know which equation represents circle C. So for this question, we should know this formula, that when you have a circle that has a center HK and a radius of R, then you could find the equation of the circle by using the formula x minus h squared plus y minus k squared equals r squared. So here they told us the coordinates of the center. So they told us the value of h and k. So I could start this off here by saying x minus h is 2, and that's being squared, plus, and then we have y minus k, but k is equal to -1. So I could write minus 1, or I could just say +1. And then this is being squared. So what I like to remember is when I'm writing the equation of the circle when I have the center, is I just take the opposite of whatever the x and y is. So I say my x is 2, so I have x and then -2, and that's being squared. And then I have y in parentheses. Instead of -1, I get +1, and that's being squared. But now I have to find the radius here. So if I look, I'm going to count the space. I could go either north, east, south, or west. So let's say we go in the direction here going north. So I'm going to count up. I'm going 1, 2, 3, 4, 5. So this tells us the radius of this circle is 5 units. So when I'm setting up my r squared, I'm going to plug in r equals 5, and this is being squared. So our full equation, if we write this out, it's going to be x minus 2 squared plus y plus 1 squared equals 5 squared is 25. And now we just scan the answer choices, and this will match up with choice 1. Question 9, on the set of axes below, triangle D prime, E prime, F prime is the image of triangle DEF. A transformation that maps triangle DEF onto triangle D prime, E prime, F prime is and we have these 4 options to choose from. So let's look through the answer choices here and see which points have to match up. So D has to go over here to D prime. And we also have over here E, this point has to go over to E prime. And then F has to go over to F prime. So whatever the rule is, it has to work for all 3 pairs of points. So let's see here. If we reflect over the line y equals x, the line y equals x goes this way like this. So I'm just going to draw in the line y equals x and ask yourself, is this acting as a line of symmetry? Well, this one here is not working because if I were to flip, let's say, point E, so this point here over the line, it would put me somewhere over here like this, and that doesn't land over here at E prime. So the line y equals x is no good. So I'm just going to cross this one off here. And now let's say we have the line y equals -x. So that would be if I drop down this line like this. So this diagonal line, I drop down like this. And it would work to map D to D prime, but the problem is E would not go over here at E prime. Okay, if I had to reflect this over, notice that it would go perpendicular to the line y equals -x. So it would go somewhere in this direction here like this. Okay, so if I drop this down, it would drop us somewhere in this location, which would miss what's going on over here. If I had to get the exact location, notice we're at 1, 2, 3, and then up 1, 2, 3, 4, 5. So we're at the point 3, 5 for point E. And if I were to reflect this point over the line y equals -x, then I could use the formula, but I'll be honest, I forget the formula, so I just know how to get there. I could just count over. I go 1, 2, 3, and then 4, 5, 6, 7, 8, and I go down 1, 2, 3, 4, 5, 6, 7, 8. So this would actually put us, let's see, at the point we'd be going to -5, -3. Okay, so we would switch x and y, and then we would go ahead and change the signs as well. Okay, so that would send, once again, the point 3, 5 over to -5 and then -3, which would not land where it needs to. So that one here is out. Okay, so we just, once again, just have to go through all this stuff here one by one, and to see which one here it has to be. So I know choice 2 now is no good. And now the next one, a point reflection. This might be tricky to remember, and let me just color point E back in as blue. But a point reflection, so for choice 3, a point reflection would be if I have, let's say this point here, I just call this W, and I want to reflect this point here through point P, then I would send it straight to point P and then straight across to the other side to W prime. So P would act as the midpoint of W prime. So that would mean the origin would have to be the midpoint of E prime, D prime, and F prime. So let's see, if I go ahead and connect all of these, so let's say I connect E to E prime, and then I connect D to D prime, and then finally F to F prime, notice that all 3 of these lines here, or these line segments, intersect right here at 0, 0. So 0, 0 would be the midpoint of D prime, E prime, and F prime. So choice 3 is definitely correct. Now, I know, let's see, the last answer choice is no good. So we could also just go through that one to see why that's no good. So if we look at the last answer choice here, so let's say I take this triangle here. So I've got this triangle over here, and I'm just going to run it through this translation here. So we're going to send this 4 units left. So we go 1, 2, 3, 4, and then 4 units down. So 1, 2, 3, 4. And notice this doesn't map onto the other triangle. So that's how I know choice 4 is no good. Definitely choice 3. Question 10, in circle O below, secants PCA and PDB are drawn from the external point P. If PA equals 17, PD equals 10, and BD equals 12, what is the length of PC to the nearest tenth? So for this one, let's see, PA is 17. So this entire segment here is 17, that's secant. And then we have PD is equal to 10, so that's this segment here on the outside. And then we have BD is equal to 12. And we want to know what is the length of PC. So that's this segment over here, which I'll put in X. And for this one here, I like to think of, we use the wee rule. Okay, so the wee rule. So let's think about that. What does that actually mean? So when I say that rule, so WE equals WE, we're saying the whole segment. So W, just so you know, stands for the whole segment. And E stands for the part that is on the outside, the exterior. Okay, so for this first part here, let's see, the whole segment would be this entire piece here, and the same thing over here. That's what we mean by the whole segment. So, and then we have next, the exterior would be the part on the outside. So just this piece and this piece over here. So let's go ahead and just set this up. So for the first part here, see how the whole segment is 17, and the exterior piece has the X. So it's 17 times X, and for that I could just say 17X. So let me just go ahead and write 17 times X equals, now over here the whole segment, so if I were to find the whole thing, I would add 12 and 10 to get 22. So I'd have 22 times the exterior segment is 10. And now all I have to do here, I have 17X equals 22 times 10 is 220. I just divide both sides by 17. So now we could just type this in, 220 divided by 17. And we're rounding to the nearest tenth. We have a 9 in the tenths place. To the right is a 4, so we round down to 12.9. So once again, X equals, we have 12.9. And we solve for X. Let's just make sure we're actually answering the question here. So the question is asking, what is the length of PC? And PC we labeled with X. So PC is definitely equal to 12.9, choice 3. Question 11, in the diagram below, CD is parallel to AB, and CB bisects angle ABD. And we want to know which statement must be true. So first what we could do is let's transfer the givens over to the picture. So we have CD is parallel to AB, and then we have CB, this segment over here, bisects angle ABD. So I could say that these two angles here are the same. But let's think very carefully about what this means when we say these segments are parallel. So when I hear segments are parallel in geometry, I'm always thinking of the beginning when we learn about parallel lines cut by a transversal. The alternate interior angles formed are congruent. And I look for a Z shape. So I'm looking for a Z like this, or a Z going backwards. And in this case, it's like we have the Z is going backwards. So what I could do is if I put a single tick mark over here, I could also label this angle here the same as this one. Okay, so what conclusion I could draw here, if CD is parallel to AB and CB is acting as a transversal, I could conclude here that angle, let's say DCB, so see angle DCB, this has to be congruent to angle ABC. Okay, so I could mark these two as the same because when we have parallel lines cut by a transversal, the alternate interior angles formed are congruent. But now let's think about this triangle that we have here. Notice that we have a triangle with two angles congruent. And if you have a triangle with two congruent angles, that means the triangle must be isosceles. So choice 4 has to be it. Question 12, line H is represented by the equation y equals 2/3 x minus 4. And we want to know which equation represents the line that is perpendicular to line H and passes through the point 6, 1. So for this one here, the big idea that we need is that perpendicular lines, the slopes are opposite reciprocals. Okay, so if we want a perpendicular line, we need slopes to be opposite reciprocals. Okay, so slopes are opposite reciprocals. And that means we're going to look for the slope of the original line and then find the opposite reciprocal. So notice here, for the starting line, we have a slope of 2/3. And I know the slope is 2/3 because I'm thinking of the formula y equals, so we have y equals mx plus b. And m is the slope and b is the y-intercept. Okay, so this is how I know the slope of our original line is 2/3, because the slope for a line is the number right in front of the x when your line is in the form of y equals mx plus b. So what we need to do, though, is take that slope and find the opposite reciprocal. So I'll say this is the slope of our perpendicular line, and I take the opposite of 2/3, which is going to be negative, and then the reciprocal tells me to flip. So my perpendicular slope is going to be 3/2. And now I could use the mx plus b formula and the point here that we were given, 6, 1. However, there's a much nicer formula for a question like this. I like this formula a lot. This is the point slope form equation. So this is another way to write the equation of a line. So you could use either this formula or this formula, but I like this one here because all of the answers are in point slope form. So that's the one I want to use. And the x1, y1 represent the x and y of the given point. So I have my x1 is equal to 6 and my y1 is equal to 1. So now I use this formula and I could say y minus y1 is equal to 1 equals the m we're going to use is not this one. We're going to use the perpendicular one because we want to write the equation of a line that is perpendicular to h. So the slope we're going to use is negative 3/2. And then we have x minus x1 is equal to 6. Okay, so when I scan for the answer choices, right away I could just eliminate these two because these have a slope of 2/3, which would be the slope we would want if we wanted a parallel line. Okay, parallel lines have slopes that are equal. So that would be for choices 1 and 2. We would be thinking of parallel lines. But see, the negative 3/2 is here. That's the one we want. And then we're going to go with x minus 6, y minus 1, choice 3. Question 13, a wooden toy block can be modeled by a pyramid with a square base as shown below. The height of the block is 17.4 centimeters, and the square base has a side length of 8.2 centimeters. The block is made of solid oak, which has a density of 0.77 grams per cubic centimeter. And we want to know what is the mass of the block to the nearest gram. So for questions like this, I remember from science that density equals mass over volume. So if we want to solve for the mass, so we want to know what is the mass, that's this value over here, what we could do is we could call this d/1 and just cross multiply, and we get the mass is equal to the density times the volume. Okay, so that's the formula we're going to use. Or you could just memorize this formula as is, but I'm able to remember d equals m/v from science, and then I just do the algebra to solve for the mass. So now first what we could do is we could solve for the volume of this pyramid. Okay, so we have a pyramid, and the volume of a pyramid is equal to 1/3 capital B times H, where B is the base area. Okay, so the base area, and they told us here that we have a square base. Okay, so if I were to draw a few dotted lines here, I can make this thing a little bit more transparent looking. So it would look, let's say, if I join it, let's say something, well, not my best artwork here, but this is what's going on here on the inside. Okay, so this would be our pyramid on the inside, and see we have our square base, which means all the sides going around the bottom are 8.2 centimeters. So what I would do is the base area, since I'm dealing with a square base, I would do 8.2 centimeters times 8.2 centimeters. Okay, so for this one, once again, capital B in this case is equal to the side length of the bottom squared. So I could start this by saying the volume equals 1/3, and then I do 8.2 centimeters. I'm gonna just make a little bit more space here. I'm gonna do 8.2 centimeters times 8.2 centimeters. This, once again, gives me the area of the base. But I also have to multiply by the height of the pyramid, which is 17.4 centimeters. Now, just know for the geometry regents, you're not graded on whether or not you use units in your answer. And if you write the units, but you write them wrong, you lose credit. But I like to show the substitution with units here, because when we multiply by the density in a moment, we're going to see how the units cancel, giving us just grams. But first, let's multiply this out. So we could start by doing 1/3, and I'll put 1/3 in parentheses like this. And then we have times 8.2 times 8.2. So I could write it twice. I can even say 8.2 squared like this. That's the same thing as doing 8.2 times 8.2. But if that's, tricky to remember, you could, of course, just write this out the long way and say 8.2 again. So I multiply these two, and then I multiply by 17.4. Okay, so we do this, and this is going to give us the volume of the pyramid, which is this value here. But to find the mass of the pyramid, I have to multiply the volume, which is this number, by the density. And they told us the density of this toy block here is 0.77 grams per cubic centimeter. So I would multiply this by, once again, 0.77 grams per cubic centimeter to get the mass. So first, I'll just write out the volume here. The volume is equal to 389.992 cubic centimeters. And the question does say to round to the nearest gram, but for geometry questions like this, please make sure that you round at the very, very end. I wouldn't round to the nearest whole number at every step, because that could throw your answer off by a little bit. So then this here is going to help me find the mass. The mass is equal to the density, which is 0.77 grams per cubic centimeter, and we're multiplying this by 389.992 cubic centimeters. And watch what happens here. The units, cubic centimeters over cubic centimeters, cancel out. And then this is what gives us our final answer here. The mass is equal to, and to the nearest gram, so the nearest whole number here, we look to the ones place is a 0, to the right is a 2. We're just going to round this down to 300 grams. Okay, and grams is the only unit left. So this is going to match up with choice 1. Question 14, in triangle ABC below, midsegment DE is drawn. If DE equals x plus 3 and AC equals 3x minus 5, what is the length of DE? So for this question here, you have to show up to the regions knowing your vocabulary, okay? The midsegment, so let me just make sure I don't cover this word here. The midsegment is the line segment that connects two midpoints of two sides of a triangle, and it has a very interesting property. The midsegment is parallel to the third side of the triangle. So that means here DE is parallel to AC, and DE is half as long as AC. So I could take DE and I can multiply it by 2. So I could say 2 times, I'll just give a little space, 2 times DE would give me the length of AC. Okay, and this is actually a theorem. The midsegment theorem once again tells us when you connect two midpoints of two sides of a triangle, the segment formed, we call the midsegment, is parallel to the third side and it's half as long. So now I'm just going to do this. I'm going to do 2 times DE. I'm going to say over here, I'll just label this as x plus 3. So we have 2 times x plus 3 is going to give us the other side here, 3x minus 5 at the bottom, or the other segment here at the bottom. So let's go ahead and work this out. So we have 2 times x plus 3 is equal to 3x minus 5. So once again, just make sure for the geometry regions that you're showing up knowing your definitions and theorems. So here, now I just distribute, and I have 2x plus 6 equals 3x minus 5. And now I go minus 2x on both sides. And that's going to cancel this out. And then I can move the constant over as well. I could go plus 5. So we go plus 5. Now we have 6 plus 5 is 11 equals 3x minus 2x is 1x. Minus 5 plus 5 cancels, so x is 11. But they were polite here to not make x equals 11 an answer choice, because what the question is actually asking for is the length of DE. So for the length of DE, now we just plug in x equals 11. DE was equal to x plus 3, so we're going to do 11 plus 3 equals 14. So our answer here is going to be choice 2. Question 15, triangle DUG is an isosceles right triangle with the right angle at G. If DU equals 10 square root 2, what is the length of GU? So for this one, let's go ahead and draw out a right triangle. And we were told in the beginning that this right triangle is isosceles, which means that the two legs are equal in measure. So these two here have to be the same. And they told us the right angle, so this part here, the right angle is at G. So if the triangle is DUG, then I could say D is over here and U is over here. I could also have written DUG this way. We would still get the same result. So now that we have this, let's go ahead and label. So DU is 10 square root 2, and this is the hypotenuse. But since these two segments here are the same, I'm going to put an X here and an X here. And now we could solve this using Pythagorean theorem. Okay, so I'm going to start off here by writing, and I'll just write this over here in this section. I could say x squared plus x squared equals, and then I take the third side, 10 square root 2, and I square this, okay? And I could do this because we were told we have a right triangle, so Pythagorean theorem applies. Now, x squared plus x squared is 2x squared, and this is equal to, and for this part, the mental math that I'm doing, if I don't want to do this with the calculator, if I'm squaring 10 radical 2, so if I do 10 radical 2 squared, that's 10 radical 2 times 10 radical 2. And really what I'm multiplying here is 10 times 10. So this starts off here as 100 times, and then I multiply square root 2 by square root 2. And square root 2 times square root 2 is equal to 2. So now I could write this over here. 2x squared is equal to 100 times 2 is 200. Divide both sides by 2. And then x squared equals 100 when I do 200 divided by 2. And now I could just take the square root of both sides. And since we're in geometry here, we're not going to write plus or minus because we're talking about the length of the side of a triangle. We're just going to say x equals 10. So that is going to be the length of GU. I just want to point out before we move on, if that mental math was a little bit annoying, what you could also do is you could take 10 square root 2 in parentheses. So I have 10 square root 2 in parentheses. I hit the right arrow to get out of here. And then I close the parenthesis and I could square it like this. And that also gives me 200. Question 16, in triangle RST below, RS equals 9 centimeters, RT equals 8 centimeters, and the measure of angle TRS equals 55 degrees. And we want to know what is the area of triangle RST to the nearest square centimeter. So for this question here, we have to know this formula. So we have triangle, let's say I have triangle ABC. So triangle ABC, I put over here, if this is angle A, then this would be lowercase a showing side A. This would be side B and side C. And the area of this triangle, so the area of triangle ABC, I could use this nice formula, 1/2 AB times sine of capital C. So this tells us here to do 1/2 A times B, but then sine of the angle C between them. Okay, so I like to think with this question here, when I'm using this formula, I think of side angle side. So notice once again that side A is over here. So I have side A, side B. And when I connect those two, notice that angle C is the one between them. So that's how I'm thinking of this formula. I'm doing 1/2 the product of two sides of a triangle times sine of the angle between. Okay, so once again, this I'll say over here in the diagram, angle C is between. So angle C is between A and B. So that's how I read this formula so that it's a little bit nicer to use. So now let's go ahead and use it. So I'm going to say here, the area of triangle RST. So this is equal to 1/2, and then I multiply 8 times 9. And then I multiply that by sine of the angle between them. And the angle between them is 55 degrees. So now we just go to the calculator, and 1/2, I could write the fraction, or I could do 0.5. So I have 0.5 times 8 times 9. I'll pretend I don't know 8 times 9 is 72. And then we have sine of 55 degrees. And I just look at the top here. Notice I still am in degree mode. So stay in degree mode for this. We press enter, and this gives us the area. So to the nearest square centimeter, that's to the nearest whole number. We look at the 9 in the ones place. To the right is a 4, so we round down to 29. Choice 3 is our answer. Question 17, triangle ABC is dilated by a scale factor of 2 to map onto its image, triangle RST, on the set of axes below. And we want to know what are the coordinates of the center of this dilation. So for this question here, I like to think of the concept of what a dilation is. So I always imagine this image here. When I have my center, so over here I'm just going to say this is our center. And let's say I have off to the side here some triangle. So let's say this triangle over here. When I dilate a triangle by, let's say, scale factor 2. So I dilate by scale factor 2. What's really going on is I'm extending a straight line from the center to all of the corners of the triangle. And then what I'm doing is I'm doubling the distance in this case because k equals 2. But I'm doubling the distance one at a time. So you see this space here, I put my new point the same distance away like this. So whatever this space is, I just repeat it and put the point of my new triangle over here. And then this point here, like let's say this was, I don't know, point W. So let me put this all in black. Like if this were W, this would be W prime. Okay, so that would be the image. And I do that for all the points. So this space here, I just repeat it, let's say out to about here. And then this one I go to about here. And then if I were to connect these, so I connect these 3 points like this, notice that I get my new triangle, which is similar to my old one. So this is the concept of what a dilation is. Okay, so if we reverse this process here, if we want to find the center of dilation, what we could do is we could take the points and their image. So I have this point, let's say in its image, and I connect a straight line and see where all the lines meet, and they will meet at the center of dilation. And you could do this with a straight edge ruler or a student ID, but one thing I have to be 100% sure of is that I'm using a point and its image. So if I'm starting at triangle ABC and I'm going onto the image triangle RST, that means A and R are going to be the points here that I want to connect. So I'm going to go like this, and I could connect them as far as I need to, but let's say I go down here. And then I repeat this process here for, let's say, point B and point S. So I'm going to connect point B and point S, and I'm going to connect them in this direction here, heading this way. So I'm going here, and it already looks like our answer is 2, 1. So this answer, once again, over here, 2, 1 is looking good. But let's see what happens when I do this to the last point. Okay, if I were to connect point C and point T. So I'll connect this last pair of points here. So I'm going to start over here at point T, and I'm going to go to point C, and I'm just going to continue on a straight line through like this. And notice that we do, in fact, connect all 3 of these lines here at the point 2, 1. So that is going to be our center of dilation. Question 18, what is the perimeter of triangle ABC where the vertices have coordinates A, -2, 3, B, -2, -1, and C, 6, -1? So for a question like this, I would definitely go to the back of the Regents and rip off the scrap graph paper, okay? So this is just going to help us here visualize what's going on. And with a straight edge ruler or even a student ID, what you could do is just make an XY axis like I'm doing right now, and then plot these points. So A is at -2, 3, so we're going left 2, up 3, and that's where A is located. Then we have B is at -2, -1. So that's going to be down here. And then C is at 6, -1. So that's to the right, 1, 2, 3, 4, 5, 6, and then down 1. So for this, what I'm noticing is that when we connect these points here, we have a right triangle. So that makes things a bit easier because when we want to find the lengths of the sides of this right triangle, what we could do is we could just count the boxes for this vertical side and this horizontal side. Now, if the right triangle was, let's say, situated like this, then we would have to use either the distance formula or some other method multiple times. But here, our right triangle, we have 2 legs that are vertical and horizontal. So this leg here, AB, we could just count is length 1, 2, 3, 4. Okay, so this is 4. And then across, we're going 1, 2, 3, 4, 5, 6, 7, 8. Okay, so far, the perimeter, which is the distance going all the way around. Okay, so the perimeter is the distance going all the way around. But so far, we have 4 plus 8. Okay, and 4 plus 8 is 12. So right away, choice 4 is looking good, but let's see what the length of the hypotenuse is. And for this one, I could use the distance formula, or I could just use the Pythagorean theorem. And let's say I just put an x over here like this. Or you know what, since we're on the xy axis, I'll use a different variable. How about we go with the letter, I'll just go with w. Okay, so I could say 4 squared plus 8 squared, the sum of the squares of the two legs, equals the square of the length of the hypotenuse. So I would have this. And now this is going to give me 16 plus 64 equals w squared. And then that gives us 80 equals w squared. And then to solve for w, just take the square root of both sides. And then we look, and the reason why square root 80 is not showing up is because this radical is being simplified. Okay, so now I break this down. If we think here, what is the biggest perfect square factor of 80? Is going to be 16. Okay, so here, I'm just going to say that w equals, since we have the square root of w squared, and square root of 80, I'm going to write as square root 16 times square root 5. And I know this because 80 equals 16 times 5. So I'm just using this property of radicals here. So this is an algebra 1 idea that we could do this when a and b are greater than a and b are greater than or equal to 0. You could split up a radical like this. So that's what's happening. And then here, w equals the square root of 16 is 4, and then we have the square root of 5. So we're going to get plus 4 times the square root of 5, which when we simplify this, we have 12 plus 4 square root 5, choice 4. Now, one thing to be very careful of here, please make sure, don't do 12 plus 4 is 16. Okay, so this would be very devastating if you did that. You could only add radicals when you have matching radical terms. Okay, so if I had something like 12 radical 5 plus 4 radical 5, then I could say 16 radical 5 because they both are like terms. But here, these are not like terms, so just choice 4. Question 19, in the diagram below, GT and PF intersect at E. And angle P is congruent to angle F, and we want to know which equation is always true. So for this one here, we have to use the idea of similar triangles. So first, I'll just transfer what we have over here. We were told that angle P is congruent to angle F. And because we have intersecting lines here, we could say that these angles here are congruent as well. Okay, when you have intersecting lines, the vertical angles that are formed are congruent. And the vertical angles are the ones that are across from each other. And then what I could say next is that these two triangles are similar by angle, which would make also, I could say the third pair of angles here are going to be congruent as well. Okay, so what I'm going to write off to the side here, I'm going to say that triangle PEG is similar to, and let's say I'm struggling with the letter arrangement here. You see how P was the angle marked in blue, and then E was marked in red, and G was marked in purple. So when I write out my next set of letters, I'm going to go blue, red, purple. So I have blue is F, and then red is E, and then purple is T. Okay, so these two triangles here are similar. And the reason why I like to do this is because the letters have to be in corresponding order, and that helps us set up the ratios that we're looking at. So let's see which equation is always true. So PE over FE. So PE and FE are definitely corresponding. So this is starting off good. PE over FE is a good start here that we're comparing corresponding sides here. And I know they're corresponding because P and E are the first two letters, F and E are the first two letters, but notice PE connects the blue to the red and FE connects blue to red. But now let's see what happens next. FT, this is the problem here. Notice that we started off in the first triangle and then went to the second triangle. So we went here, we went left, then right. But then the next ratio, see how it's starting at the triangle on the right and going back to the one on the left. So let's say here, once again, when we're setting up our ratios, we have to make sure that if we're comparing first triangle to second triangle, that in the next ratio, we go first triangle to second. So here, this order is messed up. Okay, even though FT and PG are corresponding, these would need to be flipped. Okay, so this you would have to flip, and then it would always be true. So next, let's see, GE. So I'll just get rid of what we have over here. So GE, we're going to look at next, is we have GE over TE. So GE over TE, these sides are definitely corresponding, GE over TE. They're between purple and red. Equals FT. So once again, these need to be flipped. Okay, and the reason being GE is in the first triangle. So I'll just say like that this over here, let's just call this triangle 1 and this is triangle 2. So we have triangle 1 over triangle 2, but then we're still in triangle 2 in the next ratio, so that's why they have to flip. And this answer choice is out. And now next, let's see, PE over GE. So now we're going one triangle at a time. See how PE and GE are in the same triangle. So PE over GE. So that would be, notice you have PE over GE equals, and then next we have TE over FE. The problem with this, okay, so let's really pay attention to what's going on here. PE is between blue and red. And then GE is between, we have next, so PE is over here between blue and red. And then GE is between purple and red. But then in the next ratio, the side TE over here is not between blue and red. It's between purple and red. So the correspondence is broken. Okay, so that's why this one here is not always going to be true. Okay, so this one here is out. Just by process of elimination, this is going to have to be choice 4. But let's see why that this is definitively choice 4. Well, PE over FE is we're going triangle 1 to triangle 2, and PE corresponds to FE. And then equals PG is between blue and purple, and then FT is between blue and purple. So notice we're comparing a side from triangle 1 and then triangle 2 that corresponds. And then we're going back to triangle 1 and comparing it to a side that corresponds in triangle 2. So here the correspondence is there and the order of the triangles is good. Choice 4. Question 20, a section of sidewalk in the shape of a rectangular prism is being replaced. The sidewalk is 10 feet long, 4 feet wide, and 4 inches deep. A brand of concrete mix yields 0.6 cubic foot of concrete per bag. What is the minimum number of bags of concrete mix that must be purchased to completely replace this sidewalk? So for this one here, the thing that jumps out right away is the units. So 10 feet long, so the rectangular prism here is 10 feet long, 4 feet wide, but this is the sneak attack here, 4 inches deep. And the reason why this is very sneaky is that they're telling us that the concrete mix yields 0.6 cubic foot of concrete per bag. Okay, so that's in a way our rate. Okay, we have 0.6 cubic feet of volume of concrete mix per bag. Okay, so this is like per 1 bag of concrete mix. Okay, so this is going to be something important at the end. So what we have to do is we have to find the volume of the rectangular prism. So we have, once again, I'm just going to draw out over here. So we have, this is just a piece of the sidewalk. And what we have is we're told the dimensions are the sidewalk piece here is 10 feet long. It is 4 feet wide, but then they said 4 inches deep. So over here, I'm just going to say 4 inches. I'm going to multiply that by 1 foot over 12 inches. Okay, I'm going to convert inches to feet. So there's 1 foot and 12 inches. So here, if I do 4 over 12, 4 over 12 reduces to 1/3. Okay, so just off to the side here, 4 over 12, if you divide numerator and denominator by 4, gives you 1/3. So we would get 1/3 of a foot. Okay, and see here, inches over inches cancels. This is using the idea of conversion factors from Algebra 1. So here, the other dimension here is 1/3 of a foot. The reason why we want to do this is because now when we go to find the volume, we're multiplying feet times feet times feet to get cubic feet. If you leave this in terms of inches, you're going to have square feet times inches, which is just not going to be good for this question. Okay, so the volume now for a rectangular prism, I'm just going to say over here, is length times width times height. So we're going to multiply here. We're going to have 10 feet times 4 feet. And then we're going to multiply that by 1/3 of a foot. So let's work this out. We have 10 times 4 times 1/3. And I'll just write 1/3 like this in parentheses. So we get 13.3 repeating. But now from here, what we want to do is we're going to divide by 0.6 because they told us there's 0.6 cubic feet of concrete per bag. So we'd have to take this answer here. So I'm just going to take the answer. So I'm going to go up and highlight it, press enter, and I'm going to divide it by 0.6. Okay, and we want to know what is the minimum number of bags. So this last part here is a little bit cruel. I know we look at the 0.2 repeating and we think, oh, I have to round down because this is 4 or lower, but you can't buy a fraction of a bag of concrete mix, okay? If you need 22.2 repeating, you still need this much more concrete. So that's why here you're going to have to purchase a 23rd bag, okay? You can't just buy 22 bags and then take this much and then leave the rest on the shelf. That would just be crazy, okay? So we're gonna have to buy a 23rd bag. So I'll just show the work here with the units. So the volume we found was 13.3 repeating. And then when we do feet times feet times feet, that's cubic feet like this. So what I could do with this information over here, though, is I could say if there's 0.6 cubic feet per bag, I could also say, I'll write it over here, that one bag has 0.6 cubic feet. So I could also write the rate like this. And when I want to find the number of bags, so the number of bags, I'm going to say here, and I'll just say the number of bags is equal to, we have 13.3 repeating cubic feet. And I'm just going to multiply that by the rate here, one bag. So I'm just going to say times. So we're going to go times one bag has 0.6. I'll just write this over a little more. So 0.6 cubic feet. And then you could see how the units cancel out. Cubic feet over cubic feet cancel, and we're left with just bags. And then when we did 13.3 repeating divided by 0.6, we got 22.2 repeating bags. But the problem is, once again, we can't buy just a fraction of a bag, so we'd have to round up to choice 2, okay? This type of question, though, I think is a little bit mean, because if you do all this math correct and then the last thing you do is just round improperly, it's kind of like an I gotcha question, but just read very carefully here and think application to a real-world scenario. Question 21, the line 4x minus 6y equals 24 is transformed by a dilation of scale factor 3 centered at the origin. Which equation represents the image of the line after this dilation? So for this question here, first I want to explore the concept. And this is going to help us just deal with any type of line dilation question that comes up. So let's say I have some center over here. So this is my center of dilation, and I have some line. And just to make this simpler, I'm going to scale this by scale factor 2, just so that it's easier to draw. So I'm going to take 2 points on my starting line. And what I'm going to do for this dilation is I'm just going to dilate these 2 points with this center going out scale factor 2. So I just take that same distance and I go this way. And then whatever the distance here, I go the same amount this way. And now when I connect these, okay, so I connect this point and this point, my new line is going to be parallel to my old one. Okay, so these two lines here, I'm just going to point out, these two lines here are going to have the same slope. Okay, but the y-intercepts are going to be different. So this is case 1. So this is when we have case 1. So something like this. Case 2 does happen. And when it does happen, it's a very deceptive thing that happens. So let's say I start out with some line like this, and I'm still going to go with scale factor 2. But let's say this time my center is on the line. Okay, so my center is going to be on the line. Okay, so starting off on the line. And in the first case here, our center was off the line. Okay, so that's what was going on here. And now let's say I have 2 points like this. If I scale using a scale factor 2, notice I just double the distance, and here I double the distance. All 4 of my points are on the same line. I'll just say here that the line does not change. Okay, so your answer, as hard as it might be to write it, is the exact same line that you started with. So a little mental math that I do before I really get going with this stuff, and I'll just get rid of what we have over here. So let me just make a little space from the last question, is I just quickly check to see that 0, 0, since we're looking at a center of dilation at the origin, I just quickly check that 0, 0 is not a point on this line. So I'll take x equals 0, y equals 0, and I'll plug it in. So we have 4 times 0 minus 6 times 0 equals 24. And 0 equals 24 is false. So that means our center is not on the line we're starting with. So it's going to be the first case here. So that allows me to get rolling here. And now what I'm going to do is I'm going to take 4x minus 6y equals 24. And I'm going to write it in the form of y equals mx plus b. That way we could identify the slope. Okay, I want to find the slope here. So what I'm going to do is I'm going to subtract 4x on both sides. So minus 4x on both sides. And then we have negative 6y equals negative 4x plus 24. And then we just divide everything by negative 6. Okay, so negative 6 dividing all across. And now y equals a negative over a negative is a positive. And 4 over 6 reduces to 2/3. So we have 2/3 x. And then 24 divided by negative 6 is negative 4. So that gives us 2/3 x minus 4. And what we need to happen here is, this is once again a massive idea. Our new line, so we want to find the image of the starting line. So we're going to find the image of the starting line is this one, the one that we had over here. We're going to find that image after a dilation scale factor 3 centered at 0, 0. However, the line has to change. We need to have a new line. So we need a line that has a slope of 2/3 and a y-intercept that's not equal to negative 4. So here I could just tell right away, we're narrowing it down to 1 and 2, but 2 we could chop because this would be the same line, but this would be the case where 0, 0, our center of dilation is, let's say, on that line, that the starting line would not change. Okay, but if I have to show a little bit more work, how do I know that this line here, 2/3 x minus 12 is it? Well, now what I could do is I could take the point, the y-intercept that we're starting with here. So see here, we have a y-intercept at negative 4. So I could take the y-intercept, which the full coordinates would be x is 0, y is negative 4. Okay, so that's just another thought here. When you have a y-intercept of negative 4, that's just telling you where your line is going to hit the y-axis, but the full coordinates would be 0, negative 4. And if I dilate this by a scale factor of 3, and I'll say here center, so center at 0, 0, then I just multiply the x and y by 3, and that's going to give me 0 and then negative 12. So this is my new y-intercept. Okay, so if I had to write the line, by hand, I would say, all right, y equals m, the slope does not change. So our slope, 2/3, is just going to carry along. So we have 2/3 x, and then our new y-intercept is minus 12. So that's why we're definitely going with choice 1. Question 22, a rhombus is graphed on the set of axes below. Which transformation does not carry the rhombus onto itself? So we have a bunch of options to choose from here. And the first one here, a rotation of 180 degrees about the origin. So if we rotate this shape 180 degrees about the origin, and let's say I take this point here. So this one here in the corner is at negative 1 and then up 1, 2, 3, 4. So the point negative 1, 4. If we rotate this 180 degrees about the origin, what that's going to do is it's going to send it to the point 1, negative 4. So we could just remember this rule is take the point xy and it goes to the point we would have negative x, negative y, which really just means change the signs of x and y. And that would put us over, once again, at 1 and then down 1, 2, 3, 4. So notice this one here is not a good transformation. This will not carry the rhombus onto itself because this point would have to land in the opposite corner and it's just not making it there. So right away, choice 1 is it. So let's see though, why are the other answer choices not the ones we're going with? So we have to check here, why do the remaining answer choices actually carry the rhombus onto itself? So for choice 2, we are going to rotate 180 degrees about the point 1, 0. So for something like this, if I move our center here over and I rotate 180 about this point, what I could do is I could count the rise over the run. So here to go from the purple point here to the blue one, I'm going down 1, 2, 3, 4. So I'm going down 4 and I'm going over 1, 2. And if I repeat this, if I go down 1, 2, 3, 4 and over 2, notice this puts me in the opposite corner, just like we needed to. Okay, so here, if I just draw a straight line here, see how that this models also the rotation of 180 degrees, that if I were to spin this point here in circular motion, it would go 180 degrees to this point in red. And I know it's going to go 180 because we have a straight line, and the measure of a straight angle is 180 degrees. But I like using the rise over run method here when I have to rotate 90 degrees, 180, or 270, and I'm not centered at 0, 0. So 2 actually does work, so that's why this one's out. But then if we actually look at the last 2 answer choices here, these are the equations of the diagonals of the rhombus. And the special properties of a rhombus is that the diagonals are perpendicular to each other, okay? And for any parallelogram, the diagonals bisect each other. So I could say that these 2 segments here are the same, and these 2 segments are the same. So what we could say together is that the diagonals of a rhombus are perpendicular bisectors of each other. Okay, not only do they bisect each other, but they bisect each other and form 90-degree angles. So these 2 would actually work because if these 2 line segments here are perpendicular bisectors, then that means that this point over here in purple is going to map over and across to this point in red like this, okay? And we know this is true because, once again, of the 90-degree angle and the fact that these distances have to be the same here. So those 2 pieces together tell us the purple will go to the red, and this would be for any pair of corresponding points as well. Something you could do that's a little bit extra, but you could take your actual paper and you could turn the paper so that the diagonals are facing straight up and down like this. And then this will help it be even more obvious. I'm just resize this a bit, but this will help it be even more obvious here that this diagonal line is acting as a line of reflection. And the same thing is true if I were to rotate the other way. So let's say I point this diagonal up like this. I could see that, once again, that this rhombus here is going to fold over itself over that line as well, okay? But we just have to be able to track these 2 equations also on the graph. You just look at the slopes and y-intercepts. But here we're definitely getting choice 1. Question 23, in right triangle hey below, altitude AL is drawn to hypotenuse HY. If HY equals 25 and YA equals 20, the length of AL is... And for this one, I would start by labeling. So we were told here that HY equals 25. So that's this entire segment over here is 25 units long. And this is the hypotenuse of the big right triangle. Okay, so this here just represents, I'll just label, this is the hypotenuse. And then next we're told YA is equal to 20. So this is one of the legs of the big right triangle. And we want to know what is the length of AL. So this is the piece here that we are looking for. So there's a few ways we could go forward with this, but one way would be to use the leg rule, okay? We could use the leg rule to first find the length of this segment here, LY, okay? And please don't forget the leg rule, okay? You should never skip leg day. So we have this piece over here, 20 is, we'll call that leg 1. And then I'll just do this here in a different color here. X over here would represent part 1. Okay, so now I could write out the leg rule is hypotenuse over leg 1 equals leg 1 over part 1. And now I just plug in. The hypotenuse is 25 over, let's make that a little neater. So we have 25 over leg 1 is 20 equals leg 1 is still 20 over part 1. I'm calling X for now. And from here, what I could do is I could reduce this first, or I could just cross multiply, but let's just go ahead and cross multiply. We have 25 times X equals 20 times 20 is 400. And now we just divide both sides by 25. So we could say X equals 16. Okay, so X, part 1 over here is going to be equal to 16. Now, one thing I want to point out here. So once I know what X is, so I'm just going to go ahead and get rid of this, and I will write the number 16 in. But once I know what this is, since we were told AL is the altitude, we could also say that we have 90-degree angles over here. So now that we're looking for what is the length of AL, and I already used X, so let me go ahead and put a Y over here. I could, at this point, just use Pythagorean theorem. Okay, so Pythagorean theorem will work, but there's a nicer way to do this. The nicer way to do this, I already recognize, and this is also an SAT strategy as well, is that a very common right triangle that gets drawn is the 3, 4, 5 triangle. So I'm looking at this triangle over here, and you know what, I'm just going to swap out the placement of the numbers just so that it matches directly. So here I'm going to write, let's say this side here is 3, this one is 4, and this one is 5. Okay, so same triangle, I'm just flipping it and rotating it a little bit different. But now what I'm looking at here is the corresponding side. So notice how 4 corresponds to 16. And then I have 5 is corresponding to 20. But I have to think about what would be my scale factor. How do I get from 4 to 16 and 5 to 20? Well, my scale factor would be 4. So then that tells me if I do 3 times 4, the mystery value of AL would be 12. Okay, so this is just a nice way. Once again, that's like a nice little strategy that shows up for the SAT as well that you could use to get choice 2. However, if you're looking at that and saying, hey, I don't want to do that, what's another way to get there? Well, what you could also do is you could just go ahead and set up the Pythagorean theorem. So I'm just going to move this stuff over here. So let's move this over. And if I use the Pythagorean theorem instead, I could say y squared. So that's this side over here squared. So y squared plus down here was 16 plus 16 squared. So we have plus 16 squared equals the hypotenuse is 20. So we have 20 squared. And that gives us y squared plus 256 equals 400. And then subtract 256 on both sides. And we'll have y squared equals, and 400 minus 256 is 144. And then we take the square root of both sides and we still get 12. Okay, so either way we're getting 12. I just think this one here has a little bit more style. Question 24, square ABCD has an area of 36. If the square is dilated by a scale factor of 1/2 centered at A, what is the area of its image? So for this question here, it's very tempting to just take the area 36 and multiply it by the scale factor 1/2 and say 36 times 1/2 is 18, so choice 2. But be careful, choice 2 is a very dangerous bear trap. The reason why we can't do this is because area is a 2-dimensional measurement, okay? So this is 2 dimensions. So you cannot simply just multiply by the scale factor. There is a way to involve the scale factor, and I'll show that after I show the more conceptual way. So square ABCD has an area of 36. Let me just make this a little nicer. So there's our square. And if the square has side length S, so let's say this is S and S, then S squared, side times side is S squared, equals 36, tells us the length of each side is equal to 6. Okay, so now I'm just going to go ahead and erase this over here and this over here, and I'll replace it with the number 6. So, and now I'll just name this is square A, B, C, and then D. So if we go ahead from here, all the sides are 6, and we dilate this square using this as our center of dilation, and we have a scale factor of 1/2, what that's going to do is it's going to pull everything closer to the center A. Okay, so everything is going to get pulled closer. So the distance from here to here is going to get cut in half. The distance from here to here is going to get cut in half. And we are going to wind up with a new square over here like this. So the new square, though, the side lengths are going to be 3. So the area is not going to be 18. The area of the new square is going to be equal to 3 times 3, which is equal to 9. And we're going to get choice 1. Now, the reason why the area couldn't just be multiplied by 1/2 is because the area of a square, so the area of a square is equal to S times S, or we could say S squared. So if I were to show like how do I like involve the scale factor and get right to the area, it's because we would have to multiply by the scale factor squared. Okay, so the scale factor K, if I square it, is equal to 1/2 times 1/2, 1/2 squared, which gives us 1/4. So the fast way would have just been to do 36 times 1/4, which gives us 9 right away. Okay, so if you're finding the area, the dilated image's area, you have to multiply by the scale factor squared. If you're dealing with volume, then you have to take the scale factor to the 3rd power. And the last note here is if I were to replace S with the dilated length 1/2 S, you could see that if I were to take, let's say, 1/2 S times 1/2 S, I would get 1/2 times 1/2 is 1/4, and S times S is S squared. So once again, this is why if we want to get right from the area of the original to the new area, we would have to multiply by the scale factor squared. So now we're moving on to part 2. There's 7 questions here, and each question is worth 2 credits. Question 25, triangle D prime A prime N prime is the image of triangle Dan after a translation. Explain why triangle, we'll just call this Dan prime, must be congruent to triangle Dan. So for this one, the idea that we need is that when you have a triangle or any shape and you translate it, so translating just means you slide it. So if you have a triangle and all you do is just slide it or move it, the triangle does not change size or shape, okay? So the new triangle is going to be congruent to the original. Now, the reason for this, or at least what we're going to write for the geometry regions when we're explaining, is we're going to say that a translation is a rigid motion. And a rigid motion preserves distance and angle measure. So that's why the new triangle over here is the same as the old one. Because when you move it, you're not changing the side lengths or the angles. Now, I just want to point out that the key phrases that the graders are looking for when they grade your regions is they want to see this phrase here. Rigid motion is a very powerful phrase to put in your explanation here for this question. And also when we say that the translation preserves, so we're going to preserve distance and angle measure. Okay, so these are the key phrases that when they see this in your explanation, they'll just say, okay, this is 2 out of 2. Question 26, the table below lists 5 metals and their densities. A solid metal cube has an edge length of 5 centimeters and a mass of 982.5 grams. Using the table above, determine and state the type of metal from which this cube is made. So for this one here, let's just think about what's going on. So we have a solid metal cube. So that means we're looking at something like this. So we have a cube and it's solid metal. And we're given a few details here. We're told that the edge length, so over here we have the edge length is 5 centimeters. And then we're told that the mass, so I'll say that over here, the mass is 982.5 grams. So for this one, what we're going to do is we're going to find the density of this solid metal cube and see which density it matches up with here in the table so we can say what type of metal we have. So just know that density equals mass over volume. And notice the density is expressed in grams per cubic centimeter. So that's how we know we're going to be doing the mass in grams divided by the volume we're going to find, and the units for volume here are cubic centimeters. So for one, we should know that when we're talking about a cube, so this one here, a cube has a volume of, I'll just say x to the third power, where let's say x is the length of the side of the cube. So we have an edge length of 5 centimeters. So this tells us the volume of our cube is going to be 5 centimeters raised to the third power. And if we do 5 times 5 times 5, or 5 to the third power, we get 125, and then we get cubic centimeters. Now, just know for the geometry regions, you don't have to write units when you're showing your work. You can just write the numbers. But I like to show the substitution with units when I'm teaching because it helps to highlight the concept of what's actually going on. Okay, so now what I could do is I could find the density. The density is equal to the mass of the cube, which is 982.5, and then we have grams, divided by, and then we're going to write the volume underneath, the 125 cubic centimeters. So I like to show the substitution with the units so we could see that the density here, grams per cubic centimeter, is what we're actually finding. So now we can just work this out. We have 982.5, and we're dividing by 125. So the density is 7.86, and then the units here are grams per cubic centimeter. And we just look at the table here and notice that this is going to match up with iron. Okay, so using the table above, determine and state the type of metal from which this cube is made. We could just say here that the cube is made of iron. Okay, so I'm just going to write down here, we're going to say iron is what the cube is made of. Question 27, the endpoints of segment CAS are C -3,1 and S 7,6. And we have to determine and state the coordinates of point A such that the ratio of CA to AS is 3:2. And we have the use of the set of axes below is optional. So first I'm going to do this with the formula, and then I'll do this with the graph. So here, if we have x, the x value here for the point we're looking for is equal to x1 plus, and then I'm going to say p over p plus q times x2 minus x1. And I'll explain what these terms mean here. So x1, y1 is going to be the first set here of x and y values, and then x2, y2 is going to be the second set. And the ratio here, 3 to 2, is representing the p and q values here. So p is equal to 3 and q is equal to 2. So first I'm just going to show the formula, and then I'll show why this formula works. So we could just plug in. We could say the mystery x value here for a is equal to x1 is negative 3 plus we have p over p plus q. So that's 3 over 3 plus 2 times x2 minus x1. So I'm doing 7 minus negative 3. And if we work this out, we're going to have x equals negative 3 plus 3/5. And then 7 minus negative 3 is 10. So then from here, what we could do is just simplify. 10 divided by 5 is 2. And then negative 3 plus 3 times 2, we're just going to have over here x equals negative 3 plus 6, because that's 3 times 2, which is going to give us x equals 3. Okay, so this is our x coordinate. And now when we want to find our y coordinate, we're going to say y equals, same idea, but now y1 plus fraction, and then y2 minus y1. So y1 is equal to 1, plus we're still going to get 3/5. So p over p plus q is still going to give us 3/5. But now the difference of the y values, we're doing 6 minus 1. So this gives us y equals 1 plus 3/5. Let's make that neater. So we have 3/5 of 5. 5 over 5 cancels, and 1 plus 3 is equal to 4. So our solution here, the coordinates of A is located at 3, 4. Now, before we move on, we have over here the use of the set of axes below is optional. But I'm going to use this set of axes here to highlight the concept of why this is our answer. So first I'll plot negative 3, 1. So that's over here. That's going to be point C. And then S is at 7, 6. So that's 1, 2, 3, 4, 5, 6. 7 up 1, 2, 3, 4, 5, 6. So there's S. And the concept that we need for this is that we have to think of the ratio 3 to 2. A ratio of 3 to 2 means that in total we have 5 equal parts. So next what I'm going to do is I'm going to count the rise over the run. Okay, and I can look over here and say, all right, my x2 minus x1 was equal to 10, and my y2 minus y1 was equal to 5. So that tells me I'm going to rise 5 and run 10, but I'll still count it out. We're going up 1, 2, 3, 4, 5. So I'm going up 5, and I'll do this without actually making the dots. So 1, 2, 3, 4, 5, and then over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're going up 5 and then over 10. But if we have 5 equal parts, I'm going to divide this by 5. So instead of going up 5, I'm going to go up 5 divided by 5 is 1, and over 10 divided by 5 is 2. And watch what happens. I go up 1 over 2, up 1 over 2, and now I'll actually mark the points. Up 1 over 2, up 1 over 2, and the last time I do it, I wind up at S. And notice that if I were to connect this line segment here, so I connect all these points here to make a line segment, my location of A at 3, 4, notice that A over here separates this line segment into a ratio of 3 to 2. I have 3 equal parts to the left and 2 equal parts to the right. Okay, so that's why this answer here is definitely good. Question 28, the ramp shown in the diagram below has an angle of elevation of 4.8 degrees. The ramp is built to a landing 0.6 meters above the ground. And we have to determine and state the length of the ramp to the nearest tenth of a meter. Okay, so since we're looking for the length of the ramp, that's this part over here. So I'm looking for this piece of that right triangle. So we're looking for, let's call this X. So now let's think about what we know. So this angle over here, this acute angle, we know the side opposite of 4.8 degrees. So see over here, if we go across, this side here would be the opposite side. Okay, so this side here is opposite of the 4.8 degree angle. And then X over here represents the hypotenuse. Okay, so this is the hypotenuse of the right triangle. And now I like to think of the phrase SOHCAHTOA. So SOHCAHTOA is a way to help us choose the correct trig function to find, in this case, the missing value X. So when you're saying opposite hypotenuse repeatedly, you know the opposite side, you want the hypotenuse, that's telling you to use the sine function. Okay, so we're going to use sine. And the way to interpret this, O stands for opposite, H stands for hypotenuse, A stands for adjacent. So what I'm reading this as, I say sine of theta is equal to the ratio of the side opposite of theta over the hypotenuse of the right triangle. So I'm just abbreviating this here like this. So that's what this means here in terms of the actual trig function. So now I just set up my equation. I have sine of my angle is 4.8 degrees equals, and now I'm setting up the ratio, the opposite side, which is 0.6, divided by the hypotenuse is x. And now from here, we have to solve for x. And this algebra could be a little bit tricky, but a coworker of mine came up with a cool way to solve for equations like this. This coworker calls this the swap, okay? So when you have x in the denominator of a fraction, and it's just, a single fraction like this, like some number over x equals some other term, you are allowed to just swap these two algebraically, okay? And I'll show why at the end, why we could do that. But let's just say you want to just get to the answer faster. You can say that x equals 0.6 over sine of 4.8 degrees. So now we just type this in. We have 0.6 divided by sine of 4.8 degrees. And notice we are in degree mode up here. We press enter, and we're rounding our answer to the nearest tenth. So in the tenths place, we have a 1. To the right is a 7, which is 5 or higher. So we're going to round up to 7.2. So now we can write out our final answer to the nearest tenth of a meter. We have 7.2 meters. But remember, for the geometry regents and the free response, you don't have to write the units next to your numerical values here. We can just say 7.2. Question 29, angle KML is the vertex angle of isosceles triangle KLM below. Side LM is extended through vertex M to point N. If the measure of angle K equals 15 degrees, determine and state the measure of angle KMN. So for this one here, the first theorem that jumps into mind is the exterior angles theorem. So anytime you have a triangle where you know two angles, and let's say I call this one A and B, the measure of the exterior angle that's far away from these two is A plus B. Okay, so when I know these two angles here, the one outside away from that third angle is equal to the sum of these two. So that's what I want to use here. But let's think. They told us the measure of angle K equals 15 degrees. And we might be thinking, wait, I only know the measure of one angle. So this is a phrase I tell my students to say all the time. Anytime you get stuck, let's say in a question like this, ask yourself, what information did they give me that I didn't use yet? So they told us that KLM is an isosceles triangle. Okay, they said isosceles triangle KLM below. And they said that KML is the vertex angle. So if this angle over here is 15 degrees, then this one over here has to be 15 degrees as well, okay? Because the base angles of an isosceles triangle are equal in measure. So now that we're looking for the measure of the angle on the outside here, the measure of angle KMN, so we are looking for this angle over here, all we have to do is use the exterior angles theorem. We could say the measure of angle KMN is equal to, we could do 15 degrees plus 15 degrees equals 30 degrees. Okay, this is the exterior angles theorem. Question 30, in the diagram below of circle L, the area of the shaded sector KLM is 7.5 pi and LK equals 5. And we need to determine and state the degree measure of angle KLM, the central angle of the shaded sector. So for this one, it helps to know here that if we have circle L and they're telling us LK equals 5, this value here represents the radius of circle L, okay? Because it's going from the center to a point on the circumference of the circle. So what we could do with this information, we could find the area of circle L, okay? So the area of circle L is equal to pi times the radius squared. So I could say pi times the radius is 5, and we square it, and this gives us 25 pi. But what I like to think of for questions like this is percents. Okay, so for this, I'm thinking part over whole. And if I had to turn this into a percent, I would take this decimal and multiply by 100. And that's how we would turn the decimal into a percent. But it helps here just to think that we're taking a ratio of this full circle here. So now we look at the area of the shaded sector. So the area of the shaded sector is 7.5 pi. But what we're going to do with this is we're going to find what ratio of the full circle does the 7.5 pi square units of area make up. So now I'm going to do the part So 7.5 pi over the whole area is 25 pi. Okay, so I'm just going to work this one out here. Pi over pi cancels, and now I get to see what this value works out to. So now let's just type this in. We have 7.5, and we're dividing by 25, and we get 0.3. Now, what this means in the context of the problem is that 3/10 of this circle is shaded over here. But now, there's a nice way to relate this to the measure of the central angle. If this sector here is 3/10 of the circle, then this central angle is going to be 3/10 of 360 degrees, which is the measure of a full spin of a circle. So now all I have to do is just take the 0.3 and multiply by 360 degrees, and this gives us 108 degrees. So now we can just write this all out. So this ratio here worked out to 0.3, and now I'm just going to take the 0.3 and show the work over here that I'm multiplying this by 360 degrees, which gives us 108 degrees. So I'm just going to say the answer formally. The degree measure, so the measure of angle KLM equals 108 degrees, and this is our solution. Question 31, using a compass and straight edge, construct the image of point A after a reflection over segment BC, and we have to leave all construction marks. So for this question, we have to know that a reflection is a type of transformation such that the line of reflection is the perpendicular bisector of a point and its image. Okay, so this line, like wherever A is going to land when we reflect it, let's say over here at A prime, BC has to be the perpendicular bisector of A prime. Okay, so that's the idea, but you can't just eyeball it and be like, all right, I did it. You have to do this with a compass and straight edge. So here, what I'm going to do is I'm going to place the compass over here at A, and I'm going to open the compass up, and I want to open it just enough so that when I swing the arc, it's going to hit this line segment twice. Okay, so I'm going to swing it in this direction once, and then I swing it over here in this direction, and notice that I have 2 points of intersection. But now what I want to happen here, I want the distance from A to this line to be the same as the distance from this line to A prime. So when I go looking for A prime, what I could do is first note that the distance from this point up here to A is fixed, that I'm going to swing the arc in this direction like this, and then I'm going to move the compass over here. And once again, just being mindful that the distance from that point to A hasn't changed. And I'm going to swing another arc in this direction, and this is going to tell us the location of A prime. So I could just go ahead and label this point over here as A prime. And the construction that I'm doing is I just did the technique for constructing a perpendicular line through a point that is off the line. So if I were to connect here, I don't have to do this part, but if I were to connect A over here like this over to A prime, we would be able to see here that BC is the perpendicular bisector of A prime. Okay, the distance for one from this point to A prime, so now I'll just adjust this a bit so we could see the distance from here to here is going to match the distance from the middle point here to over at A. So this line segment here is definitely the perpendicular bisector of A prime, and this would tell us where the image of point A is. So now we're moving on to part 3. There's 3 questions, and each one is worth 4 credits. Question 32, Joan wants to fill an empty 75-liter fish tank with water. She uses a cylindrical bucket with a diameter of 20 centimeters. Determine and state the maximum number of buckets of water filled to an exact height of 26 centimeters Joan can put into the fish tank before it overflows. And here we have 1,000 cubic centimeters equals 1 liter. Well, let's break this question down piece by piece. So we have Joan wants to fill an empty 75-liter fish tank with water. So the 75-liter fish tank is what's being filled with water. So let's think about what's the volume of the fish tank. So here I'm going to write over here the volume of the fish tank. So this we could find by using this information here. The 1,000 cubic centimeters equals 1 liter. So here the volume of the fish tank we could say is, I'm going to convert 75 liters into cubic centimeters. So this is from Algebra 1. We call it multiplying by conversion factors. So I can multiply 75 liters by 1,000 cubic centimeters over 1 liter like this. The units cancel, and this tells us the volume of the fish tank is going to be 75 times 1,000 is 75,000. So we have 75,000 cubic centimeters. Okay, so that's the volume of the fish tank. But we also have to know what is the volume of the cylindrical bucket that Joan is using to fill the fish tank. Okay, so the volume, I'll just say the volume of, the bucket, I'll say the volume of one bucket equals, and for this one, the formula I'm thinking of is the volume of a cylinder, which is pi r squared times h. Okay, this formula can be found at the back of your Regents. And I know I'm using this one because they told us once again over here that Joan is using a cylindrical bucket. So we're going to use the volume of a cylinder formula. So here we have pi times, but we have to be careful. They're telling us the diameter is 20 centimeters. So this would tell us then that the radius is half of that, and 20 divided by 2 is 10. So the radius would be 10 centimeters. So we're going to have pi times 10 centimeters squared, and then times the height is the height of the bucket is 26 centimeters, okay? Or the Joan is filling the buckets to an exact height of 26 centimeters. So we're talking about the volume of water inside the bucket. So the 26 centimeters goes over here. Now, just know for the Regents, you don't actually have to write the units at all as you're doing these questions, but I like to show the substitution with units just for instructional purposes. And in classes like physics, in that class, you'd have to write the units throughout the whole way. So it's good to practice this now. But at the Regents, if you want to play it safe, you don't have to write units at all, but you just have to know what you're doing with each of these numbers. So this, now I could just work out. So we're doing pi, that's secant, and then this button here, this little up arrow. So you have pi, and then 10 squared, I'll put 10 in parentheses, close the parentheses, and then square. And then I'm going to put another set of parentheses and put 26 on the inside. And this tells us the volume of one bucket is this value here. But what we're going to do is we're going to divide 75,000 by the volume of one bucket. Okay, so we're going to take the 75,000 and we're going to divide this by the answer that we just got over here. And for this one, the question is asking for determine and state the maximum number of buckets of water that Joan can put in the fish tank before it overflows. So we would have to stop at 9 buckets, because the moment you start going past 9 buckets, then the volume of the fish tank would be exceeded and it would overflow. So just 9 buckets. So we could just write this out here. We have 8168 and then 0.140899. And the units here were cubic centimeters. Okay, so cubic centimeters. That's for this part. So now just to show the rest of the work here, we're doing 75,000. Okay, so 75,000. I could write cubic centimeters and then divide by cubic centimeters and show the units cancel, but I don't have to do that here. I'm just going to divide here. 75,000 divided by, we have 8,168 point, and then the rest of the decimal, we have 140899. And this works out to, I'll just write out a bunch of digits here. We have 182. And I could stop here even and then just write my final answer from this value. So determine and state the maximum number of buckets of water. We're going to say 9 buckets. Okay, so this is the maximum number of buckets Joan can pour into the fish tank without having it overflow. Question 33, as modeled in the diagram below, 2 cables are attached from a point on a tree 12 feet above the ground. The longer cable is anchored on the ground 3 feet farther from the tree than the shorter cable is anchored. And then we have the angle of elevation between the shorter cable and the ground is 50 degrees. And first we have to determine and state to the nearest foot the distance from the base of the tree to the point where the longer cable is attached. So the question here at the end to start is asking for this length over here. So this entire distance here that I'm highlighting in purple. So what we could do is we could label this part over here. We'll call this part that I'm highlighting in pink, we'll just call that part X. And if you notice what we have 2 right triangles. And the first one I want to work with is the one in yellow. So when I look at this one, I see X. And when I think my way through this, I say X is adjacent. I'll just abbreviate adjacent to the 50-degree angle. Okay, so that's where my head goes. X is adjacent to the 50-degree angle. And I would say 12 is opposite of the 50-degree angle. Okay, so when I say opposite and adjacent, that makes me think of tangent. Okay, so then I also think of this phrase here, SOHCAHTOA. And if I'm saying opposite adjacent, then that tells me to use the tangent function. So then what I'm going to do is I'm going to say tangent of the angle 50 degrees is equal to the ratio of the side opposite of the 50-degree angle, which is 12, over the side adjacent, which is x. Okay, so we get here, and then the algebra could get a little tricky for some, but just know there's a nice little shortcut here. When you have an equation like this, you could just take these terms here, the x and the tangent 50, and you could swap them. Okay, so we could say that x is equal to 12 over tangent of 50 degrees. If you're looking at that and that bothers you, like, wait, where are you getting that from? Well, then to show the algebra, you could just write tangent 50 degrees over 1, cross multiply, and then you have x times tangent 50 degrees equals 12 times 1 is 12. And then we just divide both sides by tangent of 50 and see how it gives us the exact same thing. Okay, so this is the long way to get there, but you could just, once again, just swap these. It's a very useful trick when you are dealing with these type of trig equations. Okay, but I only need to show my work once, so I'll just get rid of what we have written over here in this section. So now from this point on, I'm just going to type this in the calculator. So we're doing 12 divided by tangent of 50 degrees. And that's going to give us this value here. So I'll just write out a few digits after the decimal. So we have x equals 10 point, then we have 0.69. And then I could say here, I'll just write the rest out, 19557. Okay, so this is what x is, but they're asking once again, determine and state, and they told us here to the nearest foot, the distance from the base of the tree to the point where the longer cable is attached. So for this one, to write out our final answer, the last thing that I'm thinking of, so I'll just think about this over here. If we round to the nearest whole number, we're going to get 10, but we also have to add the 3 feet over here, and 10 plus 3 is equal to 13. So we're just, once again, determine and state the distance from the base of the tree to the point where the longer cable is attached. I'm just going to say our final answer now is just 13 feet. Okay, so 13 feet. If you wanted to show that little work on the side, I could just say over here that 10 plus 3 is equal to 13, and then that's where our answer is coming from. So now for the last part, we have to determine and state to the nearest degree the angle of elevation between the longer cable and the ground. So the angle of this last part here, the angle of elevation between the longer cable and the ground would be this angle over here. So I'll just call this angle over here theta. Let me just make this a little bit neater. So theta is a popular letter to use when you're talking about angles, the Greek letter theta. And if we focus over here, the right triangle that contains theta is this big right triangle here, okay? The one that spans a little bit more. Let me just draw this up a little bit higher. And hang on, we could just fix this up a bit so it really matches nice. All right, so this right triangle that I'm highlighting in green is the one that's going to contain theta. All right, and then let's just move this piece up like this so it lines up very nicely. Okay, so for this one, what I'm thinking of is if we think about theta, notice that opposite, so we have theta is our angle. So I'll just say angle theta, and opposite of theta, so opposite of theta is the side that is 12 units long. And then adjacent to theta, right next to it is the side that we just found that was 13 feet long when we rounded. Okay, so we have 12 here and 13 here. So what we could say is we could say that tangent of angle theta is equal to 12 over 13. Remember, when we say opposite adjacent, we should be thinking of the tangent function. But when we want to go from this to the actual angle, we have to use the opposite of tangent, which is tangent inverse. Okay, so that's the tan with the -1 here. That means tangent inverse. And we just write the ratio 12 over 13 on the inside, and then the calculator does the rest. So to get tangent inverse, we're going to press second tangent and then write in our ratio 12 over 13. And this tells us that theta to the nearest degree is going to be 43 degrees. So I'll just write a few digits after the decimal. Theta equals 42.709, but they did say for the final answer, determine and state to the nearest degree. So our final answer to the right of the ones place is a 7, so we're going to round up to 43 degrees. So we're just going to say 43 degrees is our answer. Question 34, quadrilateral reed has vertices with coordinates r -1, 3, e 2, 7, a 10, 1, and d 7, -3. and we have to prove that read is a rectangle, and then we have the use of the set of axes below is optional. But for questions like this, I highly recommend that you use the set of axes below, because when you're able to visualize what's going on, that helps you come up with a good strategy. So R is at -1, 3. So I'm just going to go ahead and plot these points. We have E is at 2, 7. So we're just going to count up here. So we're going to go up to the point 2, 7. And then A is at 10, 1. So I'm going over 10, up 1. And then D is at 7, -3. So I could just go backwards 3. Let's see. So 9, 8, 7. And then down 1, 2, 3. And this tells us here, well, just looking at this picture, this tells us that read is definitely a rectangle. But when they say prove that read is a rectangle, please don't say, oh, I drew this out and it looks like a rectangle, therefore this is a rectangle. Like, that would not get you any points at all. So to get points, you need justification and actual theory. So there's a few ways you could do this. You could prove that read is a parallelogram and then show that you have, let's say, one right angle here at E, because a parallelogram with a right angle is a rectangle. You could show that you have a parallelogram and then the diagonals are congruent. When you have a parallelogram with congruent diagonals, that upgrades the parallelogram to a rectangle. But the way I want to go with, I'm just going to show that we have 4 right angles here. So this just involves finding the slope of the 4 line segments. So first, I'll show the slope of RE. And when you're showing this with notation, you could say lowercase m, and then let's say RE with the line segment symbol above it. This means the slope of line segment RE equals, and then I could use this set of axes below to find my slope. So I'm just going to use rise over run. So I'm going to go up 1, 2, 3, 4, and then run 1, 2, 3. So I have to rise 4 and run 3 to get from R to E. So that tells us the slope of RE. And then next I could focus on EA. So if I want to go from, let's say, E to A, the slope of EA equals, and to get from E to A, I'm going down 1, 2, 3, 4, 5, 6. So I'm going down 6. And then I'm going over from this point 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this fraction here actually reduces, if I divide top and bottom by 2, to -3/4. But then notice that these two numbers here, these numbers are opposite reciprocals. Okay, and when you have slopes that are opposite reciprocals, this tells us that RE is perpendicular to EA. But I have to make one more statement here. I can't just stop here. I have to actually say that this tells us then that angle E is a right angle. Okay, and I'll just abbreviate like this. I'll say angle E is a right angle. And now I move on to the next angle over here at A. So I already found the slope of EA, so now I can just find the slope of AD. So let's do that next. The slope of AD, this I'm just going to do rise over run, but I could start from D and go to A, is we're going up 1, 2, 3, 4, and over 1, 2, 3. So I have to go up 4, over 3. But notice these values here are also opposite reciprocals. And when your slopes are opposite reciprocals, that tells you that the line segments here are perpendicular. So EA is perpendicular to AD. And if EA is perpendicular to AD, that means that angle A is a right angle. Okay, for these types of questions, I like to use the flowchart proofs. I find that it's, much easier to organize your information this way. And now next we'll find the slope of RD. So the slope of RD, I'll write it out like this. The slope of RD equals, we're going down 1, 2, 3, 4, 5, 6. So we have a slope, we're going down 6, and then over 1, 2, 3, 4, 5, 6, 7, 8. And -6 over 8 reduces to -3/4. And notice that these two slopes here, so this one, so I have this one here, and this one here, these are opposite reciprocals. Okay, so these are opposite reciprocals, which tells us then that AD is perpendicular to RD. And if AD is perpendicular to RD, that means angle D. So this tells us that angle D is a right angle. All right, and now we have to just say one more, angle R. So notice in the beginning we said the slope of RE is 4/3. I'll just rewrite that again over here. So the slope of RE, let me just make this neater. So the slope of RE is equal to 4/3. And this information combined with this tells us, well, first we have to comment that the slopes are opposite reciprocals. So just make that a little neater. So these are, let's see, opposite. So opposite reciprocals. And this tells us that RD is perpendicular to RE. And then this would tell us that angle R is a right angle. But now we have to just summarize all this information. What does these four statements tell us? Angle E is a right angle, angle A is a right angle, angle D is a right angle, and angle R is a right angle. This tells us that read is a rectangle. Okay, so I can say, therefore, read. By the way, 3 dots means therefore. So just a nice way to abbreviate in math. So therefore, read is a rectangle because, I'll just say because, or how about, we don't even need to say therefore. I could just say read is a rectangle because. That actually sounds better grammatically. So I'll just take this part out. So read is a rectangle because it is a quadrilateral with 4 right angles. Okay, you could also use the phrase equiangular or equiangular. I gotta go look up on Google how to say that one again. But this here summarizes it nicely, just showing that you have 4 right angles. And we say, hey, read is a rectangle because it's a quadrilateral with 4 right angles. So this one goes right from quadrilateral to rectangle. So that's why I prefer to do it this way. So now we're moving on to part 4, the final boss, and this question is worth 6 credits. Question 35, in quadrilateral ABCD below, side CD is extended through D to point E, such that AFD and BFE bisect each other, and DE is congruent to DC. And we have to prove that ABCD is a parallelogram. So for the triangle proof, what you want to do first is write the givens down as your first statement. Okay, if you don't write this, you automatically lose credit. If that's all you write, you don't get anything, but you absolutely have to start by writing out the givens. So now that we have the givens written here, let's come up with the strategy. So what I like to do is transfer the given information over to the diagram and then see where it takes us. So what I'm going to do first is we start off with this phrase here, AFD and BFE bisect each other. So if AFD and BFE bisect each other, that means that AF is congruent to DF, and I could say that BF is congruent to EF. Okay, so right away, I'm seeing that these 2 triangles here, so I'll highlight them, this triangle here and this one here, I could tell right away are going to be congruent triangles, and that's something that we could make use of. So we also have intersecting line segments here, so I could say this angle here and this angle here are the same. And right away, I could have these 2 triangles highlighted in yellow are congruent by SAS. But now let's think about how does that help us ultimately prove that ABCD is a parallelogram. So what we have with this information, well, let's see. We also were told that DE is congruent to DC. So I could label these segments here, DE and DC, the same. Well, if I prove the 2 yellow triangles are congruent, then that means that DC is also going to be congruent to AB. And then I could also say here that if these 2 triangles in yellow are congruent, then these angles here are corresponding, so they have to be congruent once I prove these 2 triangles are the same. And now this is starting to close out the rest of the proof. So I have a pair of congruent alternate interior angles, which then would allow us to say that AB is parallel to ED, which would then extend all of this to the entire segment here, EDC, which I could then say AB is parallel to DC, which then gives us a parallelogram because we have one pair of opposite sides that's both congruent and parallel. Okay, so that's where my head goes with this. I just start saying a little bit more after the givens. So now let's go ahead and start off with the most obvious things were what we had in blue here. So the blue stuff, we said that AF is congruent to DF, and all in the same statement here, we'll say EF. So I'm going to say EF is congruent to BF. And the reason for this, we could say the definition of a bisector. Now, there is some debate with how to write your reason out. Like, do you have to say a segment bisector separates a line segment into two congruent segments? In the most recent Regents, or this one, the August 2025, if you look at the model responses, they use this as the gold standard, just saying definition of a bisector. So if they're saying, hey, this is a 6 out of 6, then I'm just going by New York standards here. Okay, I think like when you get this idea down, this shows that you know what's going on. So I'm okay with this being enough here. And actually, I don't have to write this as a sentence. I could just say definition of a bisector, because that's not really like a complete thought if you're, talking about English and, writing clean sentences. So we could just say definition of a bisector, and New York is okay with this being the standard as of 2025 Regents, which would extend into the 2026 Regents, since this is the new Regents, and these are the standards. Okay, so this gets things started. Now for the next part here, here's a little recommendation. I would put the number 1 here and the number 2 here and say that angle 1 is congruent to angle 2. You can say angle EFD is congruent to angle BFA, but I find a lot of students, like, they make silly mistakes here and mess up naming the angles. So you are allowed to put numbers there and name the angles with numbers. And the reason for this, we would just say vertical angles. So vertical angles are congruent. And that would now establish that we have 2 pairs of congruent sides and a pair of congruent angles. Okay, so in terms of thinking of using SAS, in statement 2, we established 2 pairs of sides congruent. And in statement 3, we established this. So now I could move on and say that triangle, and the letter arrangement here, I could say, let's say FDE. So I'll say FDE. This triangle is congruent to triangle FAB. Okay, and the reason for this is side, angle side. Okay, I could just say SAS. So now let's move on to the next part of the proof. And I just made a little space so we have room to write out the rest. So now we're moving on to statement 5. And we had this information here in pink. AB, I could say, is congruent to DE. Okay, so these 2 segments are the same. And the reason for this, I could say corresponding parts of congruent triangles are congruent. And we could abbreviate it with CPCTC. If you can't remember this, a funny way to remember it, you could also say constipated people can't take craps. All right, but don't actually write that out at the Regents. You won't get any points for that. Just abbreviate CPCTC. Okay, so now notice we've proven AB is congruent to DE, but we still have to say that AB is congruent to DC. And let's think about how we could pair that together. Well, what we have is we have DE is congruent to DC. So we have this statement. And then we just said that AB is congruent to DE. So if DE is congruent to DC and AB is congruent to DE, that would tell us that AB is congruent to DC. Okay, so we can make that as our next statement. But what's one way to establish this? Well, I could say that AB is now congruent to DC. And I'm just using substitution here. See how I am substituting? I am replacing over here. If AB is congruent to DE, I'm just substituting DE with AB. Okay, so that's all I have to say here is just substitution. Okay, so that's a nice little reason to use. And from this step, now we move on and think about what else we need to say. Well, we have to be able to say that AB is parallel to DC. But in order to do that, we have to say a little bit more. We have to first establish that these alternate interior angles here are congruent. So maybe I use the numbers again. I'll put a 3 here and a 4 over here. So for statement 7, I'll say angle 3 is congruent to angle 4. And the reason for this is they are part of the congruent triangles. See the triangles highlighted in yellow? We're still going to say CP, for this. Okay, corresponding parts of congruent triangles are congruent. And now once I establish this, what I could say next is I could say that AB, so AB is parallel to, and I'm going to say the entire side here. So this bottom side here, see how we have side EDC? I'm going to say this, that it's parallel to EDC. But then I'm going to sprinkle in this word here. So if AB is parallel to EDC, then that means that AB is also parallel to DC. All right, I'm just being extra careful by saying this because the parallelogram, the sides are AB and DC. So I want to make sure that I'm saying that here just to play it safe. And now for our reason, we could say that when two lines are cut by a transversal forming congruent alternate interior angles, that means that the two lines are parallel. And now finally, we could close this proof out. Let's think about what we've said so far. We've said that AB is congruent to DC. So we said this, that AB and DC are congruent. And then in statement 8, we just said that AB is parallel to DC. So those two highlighted components together allow us to write our conclusion. We could say that ABCD is a parallelogram. And I like to abbreviate parallelogram like this. I draw a parallelogram and I write a P inside. And the reason for this is that if one pair of opposite sides is both congruent and parallel, then that quadrilateral is a parallelogram.